I should mention there's a workshop coming up Friday and Saturday. It's extra credit in all my classes. Check this out. This is Lan Chi, who is the captain of the competition team. And everybody's welcome to come to this. And she's going to do some hacking demonstrations and help people go through some Try Hack Me. So go to that if you like. It's worth extra credit in any of my classes. And it's a good thing to do. The details are here. Friday will be in this room. And Saturday will be in the other building over there, the Harvey Britt building or something.
What are the hours?
I think it's like 10 to 2 both days. Yeah, 10 to 2 and 10 to 1. Yeah, 10 to 2 essentially both days. And the main thing is if you come on Saturday, you'll have to bring your own computer because the labs over there don't have computers. This room, we have computers. But anyway, come to either or both of those days if you like. And that'll be a good thing to do. So this is 128, and we're down to another chapter and some project demonstrations, which will be pretty easy today. We're at the last part of chapter 6, so let me bring that up. That is 128. Lex 6C is here. Okay. All right, so the last part of analyzing Android applications. And so part 3 is the understanding the security model and reverse engineering applications, which we're going to do in the project. And mitigation protections and routing, so fundamental concepts. So there are generic exploit mitigations. There's 2 ways to secure an app on an operating system. One is to improve the app itself, and the other is to improve the operating system under it. And those are the generic mitigations. For example, if you take an old app and you run it on Windows 11, it will be more secure than it would have been running on Windows XP because the underlying operating system is stronger, but there are some protections that would require recompiling the app with a more modern compiler. So the same thing's true here to make the underlying OS more secure. And Android is very closely related to Linux for all practical purposes. It's a variant of Debian. And so all these protections also apply to Linux. So stack cookies are a very important one. If you take the exploit development class here, we go through this in great detail. But if you have C code, which is the way most code is, then a buffer, array of characters can overrun. You can reserve enough room for 10 characters, but if I can put in 50 characters, it overruns and I get control of the machine. And that's a stack buffer overflow, and a stack cookie prevents that because it automatically feeds in a random value at the end of every stack frame, and if that value changes, it stops the application. It notices that something has overflowed, and it's writing where the data shouldn't be, and it prevents it. So this is a defense, which is true in modern versions of Android 1.5, pretty much all of them. And there's something that reduces integer overflows that they brought in there too. Integer overflows are also a product of using C. If you have an 8-bit variable and you go over 255, it just rolls around like an odometer and goes to 0, 1, 2, which is sort of terrible. So if you have like a length limit where things can't be longer than 10, I can make them 260 long, and it will think that's less than 10. That'll wrap around. So that's an integer overflow, another flaw in C, and they have some kind of defense against that, although I don't know exactly how it works. You've got better malloc. Malloc is how you allocate temporary storage on the heap. And this is important for data that you're going to process and then be done with and want to make room for more data. But because all these, by the way, are the fault of C. That's why in the exploit development class and my secure coding classes, we talk about why people should be moving to Rust. But in C, you have to allocate spaces with an alloc command to make room on the stack, and then you have to remember to free it. And you have to free it only once. And very often in software, there is some confusion, so you either forget to free it or you free it twice. And if you do either of those things, people can take over the machine. If you forget to free it, that's called a dangling pointer. Now there's a variable pointing to memory which is being used for a different purpose, and you can write to it and confuse the operating system. And if you free it twice, the second free can be used to execute a write operation to an arbitrary location. And we do those things in the exploit development class. So they have extensions to fix that. And here's another defense against integer overflows. And then there's format string protection. Yet another bizarre feature of the language C is when you print something, you have a format string telling it how to interpret the data as string or character or integer or floating point. And if you forget to specify the format string, the user can put in a format string which will write to arbitrary locations in memory. So you can take over the box that way just through a print statement. And no, NX is very important. NX is one of the main defenses that made Windows Vista and all later versions stronger than Windows XP. This means you can mark memory regions non-executable. And all modern operating systems, you allocate memory for a program to use, and it's either write or execute. You never let a block have both write and execute permissions. And that means you write in data that came from the user, and that's fine, but you cannot execute that data. And this stops a whole generation of attacks, where you would take some field taking data from the user, like a username or password, and you put in binary data that's executable, you'd inject it into memory and then run it. And you can't do that anymore with the NX bit turned on. And address space layout randomization is similar. Operating systems of XP and before would just take the next available memory to launch every process. And that meant you could pretty much guess where every application was running. Like a server, it'd boot up, the operating system would always take the same amount of space, and then the server process would launch. And so you could guess when you inject code where it is. So they randomized it. Now every app is randomly located in memory, and that makes it harder to guess where it is and harder to take over the box. These two together, NX and ASLR, stopped the entire generation of viruses that infected Windows XP. And it took about 2 years for the bad guys to learn how to work around them. And they have the Pwn to Own contest in Canada every year, where people have their exploits. And when they first brought out Vista, for a whole year, nobody could get in. Because these defenses were so strong, they stopped all the known attacks at that time. And it took the good guys and the bad guys a couple of years to develop workarounds. So these are very effective defenses. But there's ways around them. You'll see it if you take the exploit development class, but yeah. And this is also part of it. If you're going to use address space layout randomization, you have to recompile your old code with this option, position independent executable. The code has to be written to be relocatable. If you compile it with an old compiler, it has to run in a particular location. Now, if it has position independent executable, it can be relocated in memory arbitrarily. And that's the default now for modern code. Here's another issue. We'll do this again in the exploit development class. There are relocation records. If you call libraries from compiled code, if you think about this, you write some C code, you compile it to make a Windows app. Now, Windows apps work by calling the API calls in the operating system. You just are choosing from a menu of functions that Windows provides for you. So the operating system has a bunch of functions you can call, and your program tries to call them. Now, the operating system might get updated and change those addresses. So there's a relocation table in the kernel pointing to where the new version of that program is. The same thing on the other side. You might recompile your application with a later version of the compiler, and that might change. So there are 2 steps of relocation. When you call a function like to open a window, you call the API call to open a window, you jump to your own userland relocation table, which says where I'm going to find that in the kernel. That goes to the kernel relocation table, and then it finds the app. So both of them can be updated independently. You can update your program without changing the OS, and it'll update the redirection table to find everything, or you can update the OS without updating the program, and they can both cope. That means if you have an opportunity to write to memory, like a double free that we talked about before, or overflow on the heap, that what you can do is you can write on one of those relocation records, and now when they try to call a function like print or exit, it goes instead to an address of my choosing, which gives me the chance to take over the box. And this prevents that. It means the relocation records are read-only, they cannot be written to, which stops that kind of attack. And here's another one that fixes common C functions that have problems like string copy and sprintf. There's a set of about 10 C functions that cause most of these buffer overflows. And this is a way to replace them with more secure versions of the code. And SE Linux is a high secure version of Linux. There's a whole bunch of extra security measures added. This is to make Linux strong enough to use for military applications. That's what it's designed for, security enhanced Linux. And you can turn on some of these features. This one is a fairly weak model. If you turn it on to the most extreme model, it blocks a lot of software. So most consumer devices wouldn't want that. But they do have some SE Linux features. And you can turn on the enforcing mode here. And Here's another thing that replaces dangerous functions with stronger versions of those functions. So a lot of these defenses have come in various versions of Linux, as you can see, or various versions of Android. And it also got rid of the setuid programs. These are responsible for most local privilege escalation. In older version of Linux, like Ubuntu, maybe 5 years ago, you'll find about 10 programs that are set to run as root all the time. Because, for example, to change your password, you have to write to a protected operating system file that you don't have permissions to do. So it runs this program that escalates you to root temporarily, and that's how you do a privilege escalation. You run one of them, and you find some way to crash it, so you get stuck at the high privileges. And that's what they've removed them. There's some alternative system, and that's what these do. These remove those setuid apps that always run as root. I don't know how the new system works. I should learn one of these days what they do instead. Anyway, so that's the new defenses as various versions of Android have gone by, and those are standard defenses that you'll see in Linux and also in Windows. Most of these defenses have the same issues. So now, by default, if you have an Android phone or a tablet, you don't log in as root, unless you're getting a really cheap one, and some of them are running as root and running, but that's considered very dangerous, and if your device is set that way, Google will not let you put the Google Play Store on it. You have to meet certain security requirements, or Google will wash their hand of you and say, we're not going to let our brand name be anywhere on this device because you guys are idiots. And so you don't use root. You come in as a low privilege user. You can install apps and run them, but you can't mess with the operating system. So when you root your device, you run you hack it, you run a hacking script that finds a way to get in, and then it adds an SU binary, which lets you elevate. SU turns you into the super user. So normal Android devices don't have it, but you can add it. And all right, once you do, then here's an example of SU. It's one of these SUID. Notice normal permissions are read, write, execute for the owner, read, write, execute for people in the same group, and read, write, execute for everybody else. But this S means it's special permissions, which means it will always run as root even when launched as somebody else. So this is one of those SUID apps I was talking about. This is how you escalate to root. Even though you're not root, you run this, and now you're root. So then you have the ability to view and modify the operating system itself, which is something, of course, Google doesn't want you to do, but if you're researching and learning about the operating system, you want that, and that's where we're going to run some emulators that are rooted here, so we can mess with the operating system, but it's not something you want to do on a normal phone where you're doing important things like banking and stuff. And so SU will typically ask for permission every time it escalates. This is to prevent attackers from using it. When you run SU, it'll ask you, do you want to escalate to super user? Because if somebody is remotely turning this on, you would want to know. So that's what security it has, that's it. So in order to root your phone, the most common thing is to use an exploit, a vulnerability in the version of Android that has been found and hacks in. You can also use a different bootloader. So Gingerbreak was one of the early ones in early versions of Android. Then there was something called Exynos for Samsung devices. It was a bug in the driver for the processor that you could use to escalate to root. Then Samsung Admire had a vulnerability that could be used on certain devices, and Ace Iconia had a pre-installed binary you could use to escalate. And everybody always makes a mistake somewhere, and after a while people find them. Then there was the master key exploit. You could make a modified system app with two files having the same name and reinstall it with the same signature, because the signature only checks the first executable, but the second one is the one that really runs on the device. So you could sneak something in, and that would work for most Androids up to 4.2. There's something called Howl Root that would root a lot of devices. These just come out every few months, every year or two, they come up with another root. Now, the other thing you can do is just flash different firmware out of the device, and this is, then you boot it up differently and get in. And I don't have any projects doing this because you can't do it in an emulator. You have to have a real device. All right. And so you see the Clockwork mod is one of the modified mods. Now, these things were really common about 6 years ago and older because early versions of Android had really limited customization features and it looked kind of ugly. So a lot of people used these alternate ROMs just to make it pretty, just to have the ability to change the wallpaper and stuff. They were real popular for that reason. But of course, they have other features. They're kind of fallen into disfavor these days. I don't see these used that much anymore because modern versions of Android have a lot more beautification features. So they talk about that, Lineage OS, and what happened to these. These things have kind of fallen into disfavor. They just became unpopular. You don't really need them that much anymore. So they talk about this. All right. So anyway, what we're going to do quite a bit is reverse engineering applications. We're not really going to be compromising the base operating system because that's pretty difficult these days. What's a lot easier is to compromise the applications. So you can pull an APK from the phone. You can do APK shell, PM list packages, and that will show you all the apps on the phone. And I can use grep to get only ones that contain prog, so I see the progressive app, com.phonevalue.progressive. Then I can get the path to it, which is this, it's always in the /data folder, and then it's got a name here which includes some random characters for some reason, but that's where it is. So now that I know where it is, I can do ADB pull, and that will pull the app off the phone and put it on my Linux system, whatever system I'm running ADB from, so I can analyze it. For some reason, they do this. Every time you install an app on the phone, it saves the original APK, and then it unpacks it and installs it. So you have basically 2 copies of every app. You have the running copy, and you have the original APK available. So that's handy. You can just pull the APK off. Once you've got it off the phone, you can use APK tool to unpack it. It's a zip file, but it's a little different than an ordinary zip file, so you can't just use WinZip exactly. You need a special tool. And this takes all the pieces out of it and expands them. And then you can modify it and repackage it and put it back on the phone, and we'll do that. Another thing you can do is you can just do vulnerability scanning. You can, in fact, just upload an APK to VirusTotal, and it will scan it for you. Or you can use other products. Quark and Androbugs, we'll use them in the projects. These are other vulnerability scanners that will just scan an APK and warn you about vulnerable things it does. Like here it found what looks like an API key in there. This is extremely common that people leave secrets in the code, and they end up in the compiled version, and you can find them. It happened again last week. This was what led ultimately, it's quite common that people mishandle secrets. This is what led to the greatest supply chain breach ever, which happened about 2 weeks ago when they compromised about 12 Node Package Manager JavaScript files, which were downloaded 2 billion times a week. So many projects got the infected files, and people are still trying to clean up from it. That was done by phishing a developer. They sent a developer a message saying, something's wrong with your 2-factor, you need to resynchronize your 2-factor, and he fell for it and resynchronized it, and that gave the bad guy access to the 2-factor codes, and they were able to get in. But another common mistake is they just leave an API key lying around where people can get in. Put it in a GitHub repository or somewhere in the app. So JAGX is a program we'll use quite a bit. This is very handy. This decompiles the APK into Java. You can read the Java. And so the first thing that happens, we're going to do the Indian government app. The identity app used in India is here. And you'll see this is the Android manifest, and it specifies where the launcher is. When you first launch the app, this is the function that runs. And we'll see how we can remove the defenses from this app. It has considerable defenses, and we can turn them all off and make a poison version of the app that runs. All right. And so you can modify it. This is the kind of modification we'll do to hack into a lot of apps. This is how you steal credentials from apps. I could steal credit card numbers from apps and passwords and such. You find where it's used, which is usually not too hard. You'll usually find a useful name like password here. Like I say, I can see your source code, so you can't really hide things from me very well. And then all I have to do is figure out where it's going. You can see here the password's going in v3, and the username's going in v2. So all I have to do is put out v2 and v3, and here's my label, and this puts them in the log. So it's just going to show you stealing the credentials as you log in. Yeah?
I'm not sure how to describe this, but I think it was something related to XML or something with the website. It would, I don't know how to describe this, but the shortest version I've seen it is someone logs in with certain credentials or puts in certain characters, and they pop up on the website and they mess with the code of the website.
So you put in special characters and something goes to a website?
On a website, some websites use your name or username as part of their website banner or something like that.
Yeah, I know some people do put special characters in usernames and passwords.
But in particular, if you put in the special string characters, in particular ones that don't play nice with HTML, things happen. I'm not sure if that can be related to exploits for
Yes.
security or well, it can.
Oh, there are a bunch of exploits like that. One thing, some people like to put strange unprintable characters in their password, and then they have to type it with like the Alt key and a number. And that way it's hard for people to crack your password because they won't think of that in their password dictionary. Also, you can put special characters in a URL, like up here, there's one I saw a few days ago. You can put a character in the URL that reverses the direction of typing. So you could take a ping or an exe here, and then you could go back, and put in PNG. So it looks like an image, but it's really an executable. That's one of the tricks. You can also put a null byte in that will cause it to stop here, and there's more after it you can't see. There's a lot of dirty tricks that involve special characters, yeah.
Yeah, I was going to say, so I asked about that and where that fell under relative to code modification because some
Yeah.
strings, this is actually important when it came to login.
Yeah.
Some strings, if you punch them into certain websites, not only will the website break at worst, at best, the website breaks.
Yes.
At worst, you expose certain flaws within your security.
Oh, yes, absolutely. And special characters used a lot to bypass filters and sneak bad things in. Yep, absolutely. All right, anyway, so then after you modify the code, you just repack it with APK tool, and then you sign it with some JavaScript command or Java commands. You can create a new signature and sign it, and then you have a signed executable that will run. Now, it will not pass as an update for the existing Progressive app because you don't have the Progressive certificate, but if you tell people to uninstall the old one and install the new one fresh, it'll work. And it shouldn't work. They really should have a defense against this, but a great many apps don't, and as far as I can tell, none of the people that handle large amounts of money have bothered to protect their apps. Smarter people like NFL, the app, before it runs, it verifies that the app is intact, and if it isn't, it pops up a box saying, your app is broken, you have to put on an update, which is what they should do, but none of them have bothered yet. Yeah.
I know we touched on that in terms of economics as well, is there like a easy or hard, fast way to tell whether or not the Rubicon is passed when it comes to when the sky falls, and does it need to actually implement security?
A way to tell whether an app is secure, you say?
Is there like a way to tell when this is where we have enough, mostly because it starts actually affecting you as opposed to like, this is going to affect our users, so it's not a problem?
Well, I don't know. I can only speculate why they haven't updated it. This is a perennial thing in the whole security space. When you learn security, you will always be appalled and frustrated by the stupid things people do and wondering why they do things so sleazily and badly. And you have to get over being too outraged about it. It's the fact of life. Almost everybody is either ignorant or too busy or distracted by some other consideration. So just an appalling number of products are just very insecure. And you can report them, but most companies will never fix them because they're just not ready. Only the more mature companies will do this. And that's why we have this, CISA has put out a good document called Security Maturity Model, Maturity Levels. And there's just different levels of security. Most people are at the lowest security level where they don't even know what's going on with security or care. Then there are various steps as you go up. In fact, that's a good thing to see. Let me see if I can bring that up. Security maturity. I'm in model levels. I may have to hunt for it. This should do it. Yeah, there we are. Cybersecurity maturity model, there it is. These are vendors. It came ultimately from NIST, I think. Yeah, here's the Department of Energy. This is probably a good source for it. Yeah, the cybersecurity maturity model. There it is. And self-evaluation guide. I may not find a simple answer here, but there are like 4 standard levels. And let's see if I can find one of these that is not too mind-boggling.
I'm more surprised the website still attacks.
Yeah, let's see, preparation. Yeah, so here's there's like 4 levels, and there is a simple document somewhere, but I'm not able to find it right now, where you have no security, you have some basic protections like you're putting on updates, then you have something like an incident response plan. There's like 4 general levels, and I can find it later, but it's a good way to organize your thinking. And it came in the news again because the Department of Defense just announced this week that they're going to require that all the vendors that sell products to them be 1 or 2 levels up in the software maturity, cybersecurity maturity model, which would be a lot better, although the Department of Defense itself is at the bottom. But at least they're going to demand that their vendors do a better job. All right. Anyway, let's take a look at a Kahoot. This is 6C.
Thank you for explaining, Professor.
Yeah. And
I love these things. I hate these things. I don't know how I feel with these things.
well, yes, I think a lot of people have. Some people do them, some people hate them. Yeah, anyway, they stop people from falling asleep so much. That's all I know. Nine, 10.
Where are these keys upstairs?
Good.
How many people are there at?
Well, there's 9 people online, and what about five in the room? So usually not everybody participates. But we got 10 so far. We're doing pretty well.
I gotta say, I like the neighborhood use these first processors. Yeah. Super cool, but
Well, I might have everybody that's coming. I'll wait another measure or two. Ah, good thing I waited. All right, let's give it a shot. That's right. The Department of Defense is now the Department of War. You're correct. Anyway, all right.
it's gonna cost $1 million to college.
So where do you put a canary value? Actually, my understanding is that's only the second name. Trump couldn't change the first name without going through Congress, they said. So this is like the alternate name or something. Anyway, it gives a chance for Pete Hegseth to change his title. So it goes on the stack. The stack is where data used within one function goes temporary data, and that's usually where the overflow happens. So the canary value is there to prevent stack buffer overflows. All right. All right. What is the target of double free exploits? That's the heap. Malallocate and free create memory regions on the heap, and that's what double free exploits exploit. You write to the heap in an uncontrolled way, and you end up taking over the machine. It's more difficult than stack overflows. Stack overflows have a return pointer that controls the address next to be executed right there. The heap doesn't, so it's a more indirect process to take over the machine through the heap. We do them both in the exploit development class. Anyway, alloc and free are the functions that you use to allocate and free memory on the heap. All right, how about format string attacks? Print statements. For some ungodly reason, C includes a %n format specifier which writes to memory. I don't know why they put it there except to help hackers take over your machine. I can't think of any legitimate use for it, but it's there, and you can totally use it to take over the machine. All right, and what does the NX bit do? It lets you add permissions to memory, and typically you put it on the stack. You make the stack non-executable, so data that comes from the user can be written there, but it won't run. And you could put it on other memory regions too, but the most important one is the stack. That stops the whole generation of stack buffer overflow attacks that infected all the machines up through Windows XP. All right, so I should have some winners. Okay, 27AR. Aaron, AR that is. Aaron. All right, and Bone SF will have to tell me who they are if they want their points. That's you? You're Bone, okay. Good. Here, let me stop this recording. We've done enough of that.